Hello and welcome to this presentation on the feasibility of automated prediction of bug and non-bug issues. My name is Steffen Herbold and this is joint work with Alexander Trautsch and Fabian Trautsch, which we published in Empirical Software Engineering. So why are we investigating this topic? Because, to make it short, not every bug in an issue tracking system is really a bug, so it's not really a mistake. So what happens there is users write issues and select their type. Sometimes, say, just for trivial reasons, like they want to play around, select bug. Sometimes they just think this is a bug because it doesn't work on my machine. But really, if a software was released while Java 14 was not developed and it doesn't support Java 14, that's not a bug, that's a feature request you're having. So there are quite a few of such issues, and prior research shows that basically only 60% of the reported bugs are actually bugs, or the other way around, 40% are just not bugs, but more often than not, feature requests or other things like changes to tests or something like that. So our approach, and actually not only ours, but also from the literature, was let's use machine learning to predict whether an issue is really a bug or not. And this is actually useful for a couple of use cases. So first is for us as researchers. We often analyze data from issue trackers and analyze bugs and use the labels there to determine whether something is a bug or not. And because of these basically 40% of mislabels issues, we have a lot of noise in our data, basically 40% of feature requests or stuff like that creep in there. With a machine learning model, we could just not change anything in the issue tracker, collect the data, and afterwards correct the labels and then get more accurate data and possibly better research results. Or we could try to actively improve the issue trackers through a passive recommendation. So users write their issue, but before they select the issue type, we pre-fill this value, because prior research showed that if you pre-fill it with feature or bug, users hesitate to change this value. So they then often stick with the default value if they're not sure. So you can then passively try to guide them, but they still decide on their own. So the question we were asking ourselves is, does this really work? So we looked at the literature, what did others do? Then we did a lot of manual validation of issue types to understand this. And yeah, we got some intuitions of things that are important that might need to be considered. And we wanted to see if this manual knowledge could be incorporated in a simple way in the machine learning process to just help the machine learning. And then we wanted to benchmark everything to find out how good this works and what is the best approach. And in the state of the art, when we looked at it, we just found the usual suspects. So some neural networks, mostly LSTMs, or there were also n-gram neural networks. Then there were lots of back-of-workspace approaches, sometimes manually through keywords, but more often through a machine learning model built on top of a back of words. And there was also fast text, which is a machine learning tool from Facebook, which just takes text as input, is really fast, calculates some word embeddings, and uses a shallow neural networks and for the prediction. And we then thought, what could we do to improve? Well, on the machine learning side, we considered, well, standard text mining should be enough. But what else can we do to help the standard text mining? So first, we noted that in the literature, everybody either considered only the title, only the description, or both of them together. But this is very different information. The title is very, very short and on point, and the description is very long and gives details. Due to these different properties just in length and specificity, it means that the information from the title is more or less suppressed by the description if you consider both of this together. So instead, we said, well, let's just train separate models. One for the title, for this very short text, which basically every word is important, and one for the longer texts in the descriptions. And then, this is also just due to the properties of what is a bug. Null pointers are an example for something that's almost always a bug if it's happened. If it's a user-facing application, it's always a bug. So if Zoom would now crash, with a null pointer that would be a bug. There are some instances in libraries where it's okay that null pointers happen if they are documented, but even there, null pointers usually mean bugs within the library. So our idea was, let's just find all issues that mention a null pointer, train a model there, and then this model can focus on these corner cases where null pointers maybe are not bugs. And then we train a model for everything else that doesn't have to deal with a simple case of null pointers anymore. And the final consideration we made is, what about unvalidated training data? This idea basically comes directly from learning theory. So it basically considers, where are these 40% mislabeled bugs? Are they the same as other data, or are they different? So if they have the same distribution, then from a learning perspective, we should get the same result. If they are different, so for example, because these are corner cases where sometimes users are just not sure whether it's a bug or not, or it's a certain pattern that's repeating, then this would mean that the decision boundary that this model finds would change whether we use manually validated data or unvalidated data. Since there's a lot more unvalidated out there, it would be better if we would be good if we could be in the first case and actually utilize these large amounts of data. We then conducted a relatively complex experiment here of 5 phases, where we considered validated data, unvalidated data, 3 different data sources actually, and so on and so on. So this would be too much for the 10 minutes we have here. So instead, if you're interested in our experiments and the detail, please look at the article. Instead, I want to summarize the main results. And first of all, what was the best model? Well, it was consistently fast text. And the best variant was when we used a separate model for the title and the description. And this was then about as good as the developers, which doesn't mean it was perfect, but that the errors it made were similar to the errors that developers do. So it's very good at finding bugs, but there are some predictions there that are just not bugs, but not more often than with developers. So we were happy because this sort of works. And with the validated and unvalidated data, there it got really interesting. Because with manually validated data, that's the effect that we had relatively precise models. So if they predicted something as a bug, it usually was a bug, but they missed some bugs. So this is a type 2 error. On the other hand, when we use the unvalidated data, we had too many bugs, but we basically found nearly all bugs. So, but we had more or less the same mistakes that developers did. So too many, but not exactly as many as developers. So it was a bit better there. So this was actually introducing type 1 errors. But the good part is if you find all bugs, but then can clean some data that basically some bugs you identify as you're not really a bug, this would be something where we as researchers would only gain. So our data would be less noisy. We would still have noise in there, but less than before. Similar in issue tracking systems, you would still have wrong values that you pre-fill there, but you sometimes would add the correct value there, and maybe then this would lead to better data. So it's really worthwhile to use the unvalidated data. So in summary, the most important aspects are not every bug is a mistake. That's in an issue tracking system, so don't assume that. Manual validated. You can really use machine learning to get better data. We were happy there, and we actually now want to see whether this also works in industrial practice, because it's an open question of whether developers accept this sort of guidance and whether this actually improves the model. So we're interested in doing a user study there where we directly combine this with additional aspects like bug localization. So if you're running a Jira or using GitHub Enterprises and are interested in using this within your company, please contact me. So thank you for your attention.
Hello, and welcome back to the live session. I am here with Steffen Herbold. that just presented you his work on the feasibility of automated prediction of bug and non-bug issues that has been published in Empirical Software Engineering, correct?
Yes.
So you know by now that we can answer your question. If you write them in the chat, please, I can read the question for you to Steffen. And as usual, to fill the empty waiting, I have some question that is somehow related also to something that the previous presentation said. So when you predict the bug, when you make the prediction based on bug report, the information the bug report could include information that is in addition to the text, other info. So the previous author, for instance, was talking about screenshot. So do you also use or plan to use other info that are not textual with your approach?
Yeah, we intentionally avoided that because we wanted to know whether with only the description we can already predict this, because the prediction is always available. In any issue tracking system, you always have the prediction. If we would rely on fields, this would mean that it would be different for, let's say, GitHub issues and Jira and Bugzilla. So that was the one reason. And the other reason is that if we want to pre-fill this, for example, passively within an issue tracker, then we shouldn't rely on users to first enter a lot of data and then finally we pre-fill one value. It's more like maybe a wizard or something like that, where you start with entering, please enter title and description, and then you say, okay, now enter more information. And then we could say, okay, now we put here feature or bug passively, and they won't even recognize that we modify this based on their description. So it would be very smooth, and this only works if we don't rely on many fields. So it's easier to transfer, and it's also more realistic in terms of use cases within issue trackers.
I see. Okay, so in the previous paper instead, the author was trying also to incorporate more knowledge, and also somehow related. Maybe your previous answer was somehow answering already, but could be appropriate, could be useful to specialize the prediction to more specific indicator from a domain. For instance, some word, some text could be specific to some application domain.
Yeah, certainly. So one thing you definitely need to account is the programming language. So exceptions are, for example, very good indicators that something is really a bug, especially if it's a null pointer or something like that. Or in Python, you have also certain exceptions that are maybe not bugs, like if you have a value error, that's usually a mistake by the user. But if you have other types of errors, then it's probably something that crashed. So you need to know when you train this predictor, this domain-specific stuff from the language. And also, if you can train on older issues from the same project, it will probably also increase your performance. We avoided that because we wanted to be conservative. So we choose a pure cross-project approach. Also because you have more data available. So for a text mining approach, if you have just 100 issues or something like that, that's nothing. So even in cross-project, we had like 10,000, which is not that much text when it comes to natural language processing. So it could work, it could improve this, but probably only for very large projects or when you have a lot of issues from the same domain.
Okay. Thank you for the presentation. Did you find the differences between, this is from Aurora, did you find the differences between issues incorrectly labeled as bugs across projects? Would this affect the learning? I mean, you might identify projects less accurate and discard them for learning.
So there were huge differences between projects, and there were especially some projects where the developers were really random with their labels. So that's why, so we noticed that when we did the manual validation earlier, so we used manually validated data, and that's where we got the mislabels. But there were projects that sometimes labeled, we need to make release 1.10 as a bug. So for them, the release was literally a bug in their issue tracker. So that project had then a very different distribution between labels. So there were a lot more mislabels for that project than for other projects. But when we looked at the data in terms of accuracy, that wasn't that much of an issue. So because when we trained it on manually validated data, we were able to distinguish between that, well, quite well. So the precision was not perfect, but it was okayish. The recall was also okayish. And when we trained with just huge amounts of unvalidated data, it really didn't matter anymore because there our recall was very good, always, for all projects. And our precision was, let's say, slightly better or a bit better, at least also significantly better than, let's say, doing it randomly. So we were then on the level of the developer. So we were basically doing it more or less exactly like the developers did without machine learning. And also, again, across all projects, even the ones that were, let's say, interesting in their strategy to label issues.
Okay. Hope this answered Aurora. And there are other questions from the audience. We have still time maybe for question. Or we can you can continue discussing in the discussion room. Let's wait if there are more questions. Okay, it seems we are done, Steffen.
Yeah. So
okay,
one aspect about this paper that, well, more or less follow-up work. So one guidance we have in the paper is that it's not really up to date anymore from our perspective. So we said in the paper we did not find any deep learning approach that is really good here. But right now we're finding that pre-trained transformer models might be good. So they might actually work better than everything we have in that paper, but only if it's a pre-trained transformer from the software engineering domain. So don't use pre-trained models from the general domain for this kind of problem.
Oh, we have another one. I am not aware, Oscar Chaparro, I am not really aware of projects that use automated detection of bugs and non-bugs. Maybe there are, and I am not familiar with them. Do you know of any project, or do you know why projects have not adopted these tools in practice?
So great question. I try to answer quickly. I'm not sure if anybody is using that for this kind of issue. What I know is that a lot of organizations are using automated tagging of issues in support systems. So if you have an automated support, we had talks about triage that's automated, but there's also trying to toss issues automatically to divisions and so on. That's also sometimes tagged, and they try, I know at least one here in Göttingen, where I'm currently living, that also tries to identify their bugs that way. But to the best of my knowledge, there is by now the GitHub bot that we also have there in the paper by Carlos et al. That you could use. But I don't know, for example, if there's a Jira integration or something like that. That's also something where we are looking at right now. How can we integrate this better into tooling, because we find that we are actually good enough because we're similar to developers.
Okay, good. Just time to thank you